Okay, so chapter 4.1, random variable averages and statistics. So we're going to be talking a lot about probability again in this chapter. So if you've missed anything, this is sort of a good recap for you. But let's get into it. Let's just go through this PowerPoint. Let's go through what we did in class. Okay, so what do gamblers, business managers, and students have in common? Well, they're all very interested in numerical probabilities. Okay, they want to understand whether their odds are in their favor. So in certain circumstances, gamblers want to know if they gamble on a game, what their likelihood of winning is, and how much they could potentially win or lose, if it's worth gambling on or if it's not worth gambling on. Business managers want to know if they still have a business, so they got to kind of, they got their own statistical analysis to sort of figure out. And students, of course, are interested in grade point averages, so they're all interested in some sort of numerical value. Example 1. So let's read the problem and I'll explain what it's asking and what we're going to do to solve it. So consider the following simple lottery. You pay $1 to play, and then you select an integer in the set 0 to 9. So keep in mind that is 10 numbers there. 0 counts as a number, so there are 10 numbers there. Next, the person running the lottery randomly picks an integer from the same set. If they pick the same number as you, then you win $5. If you don't, if they pick a different number, then you win nothing. So you play this game many times. How much would you expect to win or lose? Of course, it's gambling, so you're probably going to lose money. But let's talk about how much money you expect to lose per play, essentially. So each time you play and lose, you're going to lose $1. Now, each time you play and you win, you're going to win $4 on average because you paid $1 to play and you get $5 back. So your net winnings is $4. Now, your chances of winning are 1 in 10, right? You pick a number, there's 10 numbers there, and there's a 1 in 10 chance that the next person picks that same number. So your odds of winning are 1 out of 10. So let's say you play the game 10 times. Now, theoretically, of course, it could be different in the real world, but theoretically, if you play the game 10 times, you're expected to win once and lose 9 times. That's just a theoretical probability there. You play 10 times, you're expected to win once and lose 9 times. Now, if that happens, that is your expected outcome. Of course, like I said, you could win more, you might not win at all. That's what we're expecting statistically. That means if you lose 9 times, you're going to be losing $9. And that one time that you win, you will win $4. So you play 10 times and you end up losing $9 and you end up winning $4. So that's a net loss of $5. So every 10 times you play, you lose $5. Anyway, shouldn't be writing. I don't need to write on this thing. Anyway, who needs this stuff, right? So every 10 times you play, you win $4, but you lose 9. So that's a net loss of $5. So every time, if you lose $5 in 10 plays, then you're losing 50 cents a play on average, right? If you play it 10 times and you lose a total of $5, and you're losing about 50 cents each time you play. So that's sort of what our net loss is. Every time we play, we lose 50 cents. Or basically, think of it this way. Every time the person who runs this lottery plays, they're expecting to win 50 cents every time. So if you're a lottery company or a lottery business, so to speak, although it's not really a business, let's say, you have 1,000 people who come to play your lottery, then you're expecting, because they're going to lose 50 cents roughly each time they play, you're going to win 50 cents roughly each time they play. So imagine 1,000 people come in. On average, that means you're going to get about 50 cents per person. So if 1,000 people play your lottery, you're going to win $500, or you as a lottery business running it would make $500. Of course, because obviously people are going to lose money more than they win. So But the point is that you're losing 50 cents on average. So example 2, suppose that the following game is proposed by a friend. A fair die is to be rolled, and if an outcome of 2, 3, 4, 5 occurs, then your friend will pay you $1.50. If either a 1 or 6 occurs, then you pay your friend the amount in dollars equal to that outcome. So if you roll a 1, you pay your friend $1. If you roll a 6, you pay your friend $6. If you play the game many times, how much gain or loss should you expect? So this is kind of a tough one to just think off the top of your head because, a 2, 3, 4, 5 is rolled, you're winning $1.50. You just really hope that you don't roll a 6, because if you roll a 6, then you're paying $6. So let's kind of see if this game's in our favor or not. So if we create a table to help us out, these are the different outcomes that we can roll on the die, right? We can roll a 1, 2, 3, 4, 5, or 6. Those are the outcomes. This, in future parts of this PowerPoint, we're going to call X will be our random variable. This is how much we end up walking away from this game with, whether we lose money or we win money. So if we roll a 1, we're going to lose $1. So that's why it's -1 there. If we roll a 2, 3, 4, or 5, we're going to win $1.50 on any of those rolls. And if we roll a 6, we'll lose $6. And of course, the probability of each of those outcomes, there's a 1 in 6 chance for each die roll. But of course, if you're looking at this, there's a 1 in 6 chance that you lose $1. There's a 1 in 6 chance you lose $6. And there's a 4 in 6 chance that you win $1.50, because 4 out of those 6 outcomes would result in you winning $1.50. But per play, so let's assume you play 6 times. If you were to play 6 times and theoretically one result each shows up, one of those 6 times you're likely to roll a 1, which means you would lose $1. 4 out of those 6 times you're expecting to win $1.50. And then 1 out of those 6 times you're expecting to lose $6. So if you total it up, if you play 6 times, you would win $1.50 4 times, which is $6. That's winning $6 there. But you might also lose $1 and lose $6. So in total, you might lose $7. So if you play the game 6 times, you're expected to win $6, because that's $1.50, 4 times. So that'd be your winning. But there's also that time when you roll a 1. When you roll a 1, you're going to lose $1. When you roll a 6, you're going to lose $6. So those two results together mean you lose $7. So if you play 6 times, you're going to win $6 but lose $7, which means your average loss is $1. Every 6 times you play, you're going to lose $1, roughly, right? Which means you'd lose, whatever 1 divided by 6 is. That's like, what amount of change is that? Like 15, 18 kind of. 1 divided by 6, about 17 cents per play. 1/6 of $1 per play. You're losing money every time you play the game, in theory. Your average is a loss. You're losing 17 cents per play, but you're really losing $1 every 6 times you play. So if you play 600 times, remember, you're averaging to lose $1 every 6 times. So if you play 600 times, you would lose $100, because 600 divided by 6 is that 100. So you'd lose $100 if you played the game 600 times. In theory, of course. So a random variable, moving on from that, on a sample space S is an assignment of real numbers to an element of S, exactly one number assigned to each outcome. So basically, what I sum it up as is it's sort of the end result. It's sort of like your outcome. So in the last example, with the money, random variables are -1, plus 150, and -6, because those are the different outcomes. If you play that game where you roll the die, you're either going to walk away losing $1, walk away winning $1.50, or walk away losing $6. Those are the only 3 outcomes you have. So those would be your random variables. So random variable is easy to identify because it's either going to tell you what it is, or it's going to be sort of that type of outcome. So an example, if you flip a coin 4 times, right, the different outcomes of landing heads, if you flip a coin 4 times, you could have, no heads. They could have all been tails. So 0 is a random variable because 0 is one of those outcomes. You could have no heads. You could flip it 4 times and get 1 head. You could flip it 4 times and get 2, 3, or 4. But those are the different amounts of heads that you could get by flipping a coin 4 times. So these are all the different outcomes that we list here. So those are our random variables. And then over here is the probability of each of those outcomes. We're not going to find the probability there, but those are the probabilities of rolling a 0, 1, 2, 3, or 4 heads. And this is back on the example that we looked at previously. So again, your random variables are the amounts of money you win or lose. So you either lose $6, you lose $1, or you win $1.50. And then those are the probabilities of each of those outcomes, right? 1 out of 6 chance because you roll a 6 only 1 out of 6 times. 1 out of 6 chance because you roll a 1 out of 6 times. And this last one was a 4 out of 6 chance because remember, you win $1.50 if you land a 2, 3, 4, or 5, which is 4 out of the 6 ways to roll a die. So probability density function is just it's a table. It's basically a table we just looked at. Like this right here is a probability density function. This is a probability density function. It's just associating your outcome with the probability for that outcome. So if you go back to the very first problem we did where we play that lottery, remember, so the random variable is losing $1 or winning $4. Because in that lottery, let me just go back. In that lottery, you either win $4 or you lose $1. You play the lottery and you either win, which means you get $4, or you lose, which means you lose $1. So there's only 2 outcomes. You either walk away from this lottery winning some money or losing $1. So that's why there's this outcome here. Those are your outcomes. You either lose $1 or you win 4. And because there's a 1 in 10 chance of you winning, that means that there's a 9 in 10 chance of you losing. So a 9 in 10 chance you lose $1, or 1 in 10 chance you win 4. So that's the probability density function for that. First example. So Max has an alarm clock that goes off at the time he sets with probability 0.8. So the probability his alarm goes off is 0.8, or 80% chance it goes off. Sunday, he sets it for the following Monday, Wednesday, and Friday. So he sets it for 3 days. View the situation as an experiment where the results alarm goes off or alarm doesn't go off for each of the 3 days. A random variable x is defined as the number of days the alarm goes off at the set times. Assume a Bernoulli process and find the density function of x. So for our density function, remember density function is just a table. It's our outcomes and then the probability associated with those outcomes. So what are the outcomes here? Well, the outcomes are how many days the alarm goes off. Now, he sets the alarm for 3 days. The alarm could go off on none of those days. It is possible, although unlikely. The alarm could only go off on 1 day. It could go off on 2 of those days, or it could go off on all 3 days. But those are your x values. Those are your random variables. Those are the different outcomes we could have for our alarm going off. Now, it does say it's a Bernoulli process. So our Bernoulli formula is a combination n choose r, p to the r power, and q to the n minus r power. So remember, you're just going to use your calculator to evaluate this. You're going to plug that in the calculator and let the calculator give you the result. But let's talk about how this formula applies to each of these. So I'm going to use that formula to find the probability of 0 outcomes first. So the probability that the alarm works on 0 of those 3 days, just using our formula, we have the combination of n choose r. Now, n, remember, is the total trials. So since he's setting it for 3 different days, that's 3 in total. So that's our total number of trials. N is the number of outcomes in total, right? So 3 days he sets the alarm, 3 days the alarm could go off. So that's our n. R is specific to our probability here. So we're looking for 0 days it went off. So R is going to be 0 in this case. P is the probability of success, which is mentioned here. The probability of success is 0.8. Q is the probability of failure. Well, let's get the R first. So this is 0.8 So R, we mentioned, is 0 in this problem, right? So it's to the 0 power. All right, back to Q. Q is the probability of failure. Now, if the probability of success is 0.8, then the probability of failure is 0.2, because the probability has to add up to 1. So 1 minus 0.8 is 0.2. So that's how you know the probability of failure is 0.2. Oops. So it doesn't say that in the problem, but we can decipher that because we know the probability of success is 0.8, which by 1 minus that, we know the probability of failure is 0.2. Now, n minus r. N we said was 3, and r was 0, so 3 minus 0 is just 3. So that's the formula I would plug in the calculator. And I think in the calculator that gives us 0.008 probability, which is a very, very small probability, less than a 1% chance. So we just repeat this formula for the other values, except a small little changes with R. 3 is still the same because there's still 3 days that we're setting the alarm. But now if I want to find the probability of 1 day the alarm goes off, then I'm going to use R as 1. Obviously, the probability of success and failure still remain the same, but of course the exponents are going to change. So R is 1 here, and then n minus R would be 3 minus 1, so that would be 2 there for that exponent. And so that's the formula you'd plug in. So these are pretty much the same. It's just the n value changes based on, of course, whether you're trying to find 0 days, 1 days, 2 or 3 days. Those are your R values, remember, so they change on each of these. So this would be 0.8 to the second power, 0.2 to the first, 0.8 to the third power, and 0.2 to the 0 power, because 3 minus 3 would be 0. And if you type those in the calculator, you would get 0.9 or 0.096 there, 0.384, and then the last one would be 0.512. So these are the probabilities that your alarm works that number of times. So it's a pretty decent chance that it'll work all 3 days, but there's also a pretty good chance that it'll only work 2 of those 3 days. Obviously, these probability of 1 or 0 is very, very small, but I guess, technically those could happen. All right, so again, that is the probability density function. It's just this table here. So a student has 3 blank CDs and 5 CDs that contain files. So keep in mind, 3 blank and 5 with files, that's a total of 8 CDs. Suppose 3 CDs are selected at random and a random variable x defined by the number of blank CDs selected. Find the density function of x. So remember, x will be our different types of outcomes, and then we'll associate the probability of that. That will make our density function, our table. So x is defined as the number of blank CDs. So remember, we're choosing 3 CDs. So in those 3 CDs, I could possibly have chosen 0 blank CDs, right? All 3 of them could be CDs with files. So that's one possibility, is that I choose these 3 CDs and none of them are blank. Or I choose the 3 CDs and one of them is blank. Choose the 3 CDs, 2 of them could be blank. Or I choose 3 CDs and all 3 of them could be blank. So those are the possibilities. Those are our variables. Those are different outcomes of how many blank CDs we could have picked. Now the probability gets a little more interesting. So because we're choosing CDs, we're grabbing some out of a stack. This results in our combination. So because of this, we want to know how many ways there are in total to choose CDs. So remember, there are 8 CDs that we have, and we're going to choose 3 of them. So if we want to know how many ways we could do that in total, well, that's the combination of 8 choose 3. So again, that we can just type that in the calculator, and I believe when we type that in the calculator, that gives us 56. So there are 50. Each of these are out of 56 ways in total. So remember, when we rolled the die, there was only 6 ways to roll a die, so all those probabilities were something out of 6. Well, this has 56 different ways. There's 8 CDs, and you're going to choose 3 of them. There are 56 different combinations of ways you can pick those 3 CDs. But of course, we want to know how many of those ways have 0 blanks, 1 blank, 2 blank, or 3 blanks. So to find out how many of them are 0 blanks, we're going to use combination. And notice that there are, if I choose 0 blanks, that means I'm choosing 3 with files, right? 0 blanks, then the 3 CDs I've chosen are all 3 with files. So the combination for that is, well, there's one for each of them. One for blanks and one for files. There are 3 blanks in total to pick from, and you're choosing none of them in this situation. There are 5 with files, and you're choosing 3 of them in this situation. So if you just multiply those 2 combinations together, you get your total, which I believe is 10. All right, so now the next outcome is you choose 1 blank. Now remember, if you chose 1 blank, then that means the other 2 files or the other 2 CDs have files in them. So remember, you're choosing 3 CDs. So this is a situation where 1 CD is blank and 2 of them are with files. So the combination there, let's start with the blank. Now remember, there's still 3 blank files, or I'm sorry, CDs. There are 3 blank CDs. And in this case, you're going to choose 1 of them. And you're going to multiply that with the combination of choosing 2 with files. So remember, there's 5 with files, and you're going to choose 2 of them in this case. So remember, this combination says, hey, there are 3 blank CDs, and you're choosing 1 of them. There are 5 file CDs, and you're choosing 2 of them. And that's going to be the probability for this outcome, which I believe is 30. All right. So now the next one would be 2 blank CDs and 1 with files. So it's combination. There's still 3 blank, but you're going to choose 2. And there are still 5 with files, but you're going to choose 1. So this is 15. So again, the calculator is just going to multiply that together. And if you need me to show you how to type that in the calculator again, let me know, because I can do that pretty easily. I don't have a calculator on my screen right now, so I can't really show you, but see me in class if you want to remind you how to do that. So the last one is 3 blank CDs, and if they're all blank, that means 0 of them have files on it. So 3 blank, 0 files, that's a combination of 3 blank, choosing all 3 of them, and a combination of 5 with files, but you're choosing none of them. So that case, it's only going to equal 1. Now, if you want to see if you did this right, remember, there's 56 ways in total. So 10, 30, 15, and 1 all add up to that 56. So it all adds up to 1. 56 out of 56, everything's been accounted for. So, but this is the end of the problem. That's our density function. All right, that's going to cover it for section 4.1. I'll see you guys in section 4.2.